Hello and welcome back to part 5 of the Q Learning tutorial series. Thanks for checking back in. Today we are going to start on the actual training function. I've been super excited for this. I hope you have too, because we will finally actually end up with an agent that can play Atari games, which, I think is super cool. So let's get to it. If you haven't checked out parts 1 through 4, definitely check those out. It should be in a playlist with this on my channel. So essentially what we did last time was we finally got if I remember correctly, we got the data formatted, and then we got this training loop working. But a training loop's kind of useless if you're not actually doing any training. So the first thing I want to do though, before we even code the training, is I want to make sure we're all on the same page and help you guys, if you haven't looked at this before, help you understand what update we use and why we use it. I'm not just going to give it to you. I'm going to walk through the actual math and explain it to you. Now, I can only go so in depth with the time I have, but I want to look at a few equations that came up in the main paper so I can sort of explain them piece by piece, and hopefully it will help you if you're ever reading papers or anything like that, understand them in the future if you don't already. So let's make a new little cell for that. We will make this a markdown cell, and we will put some irrelevant equations in here. So in the first video, the introduction to, or sort of Q Learning explained video, I explained a little bit about what, a reward signal is and what, expected return is, but not too much. So I want to formalize it a little bit. So the first equation, sorry, it's an image. Let's zoom in to make sure you can see this very well. This is called the expected return. We usually use a G to denote it, and it's everything from from time step T, what you expect to get, basically the discounted reward you expect to get. It can be simply written as this, but it's from now to the end of the episode, or if it continues on forever, then going forever. How much reward do we expect to get? Discounted, right? So the discounted means that for every time step ahead, we multiply this by an extra gamma, which will make this smaller. So the rewards get smaller and smaller. So for example, if we got the rewards 1, 2, and then 3, and we're trying to get the G of the first time step, right? It would be 1 times 2. If our gamma's, let's say 0.95 times 0.95, this should be a plus 3 times 0.95 times 0.95, or I guess I can just put 0.95 squared. And our G, oh no. And in this case, G would be that. So you can see we're giving, the higher the gamma is, the higher weighting we put on future rewards. But this way we can G is kind of what we're trying to maximize, right? And we put the sort of discount in there to also take into account future time steps, but not maybe as much as the current time step. So this is called the sort of returns, right? So the next thing we want to look at is building on this a little bit. This is what the Q function actually looks like when written out mathematically. Now there are other ways to write it, but this is in terms of the returns, right? So it's the expected value of the return, given that we start with state S and start by taking action A, and then follow up by using this policy. Now, what does that actually mean, right? So it's starting from state S. That makes sense, right? So maybe it's the first state. So if we take the Q value of the first state, and then we also have to put in an action. So this is very key to Q values, right? You need a state and an action. You can't just have one or the other. A Q value is the expected return. If you start in a certain state, say the start state, you take a certain action, say maybe action number 2, and then so you get some reward from that, right? And then after that sort of step you take, everything after that should follow whatever policy you have. So in our case, our policy we decided was going to be if a random number, we'll use a random action some of the time, but most of the time we'll choose the actions with the highest Q value. So that's what this Q value should represent. It should represent if we start from state S and take action A, but then after that follow this policy, what do we expect to get in return? What discounted reward do we expect? And this is just another way of writing it a little more if we kind of just copy and paste this right into here. or copy and paste this right into here, we get this. So that's the actual definition of a Q value, or I guess one way to define it. So now let me get this. Sorry, I have like all these equations right here I prepared. Some of these I've written out painstakingly in LaTeX. I hope it's worth it. Hope it helps you understand. So this is sort of our policy, a little bit more formally written. Right down here, we kind of informally wrote it. But so remember, pi denotes the policy, or how we choose our actions, and this is kind of the policy we're using. So we say if epsilon, which is a value we determine, is less than some random number, then we want to use a random action. Otherwise, we want to use whatever state has the highest Q value. This argmax essentially means we look at all the Q values. So maybe there's 4 Q values. We take the position of the one, or sorry, no, it means we basically maximize the Q value and return the value for A. Oh, yeah. So we by differentiating the A in this, we try every different type of A in this function. So we try every different Q value for every action, and then return the action that gives us the highest Q value. This is essentially what's written right here. Hopefully that wasn't more confusing. But the reason I bring this up is because this will be very important right now when we're going to look at the actual sort of training function, or our loss function. So we're very close to that. There's just one other formula before we get there, directly related. And this is another way to write the Q value. And again, I do want to apologize if there's any mistakes here. Definitely comment it, and I'll pin if there is anything, because I did write these formulas by myself, so there might be something. Just a side note there. But this is another way to write the Q value, right? So if we want to write the Q value for S of t at time A, assuming we're using this policy, then what we do is we take the reward, right? Because we take the reward from this state and we add it to the reward from the next state discounted and the one after that discounted. But what's that? That's essentially the expected return from the state after us discounted, which is the same as the Q value. So the Q value can kind of be expressed recursively, right? And you can try and derive this from this function right here, or this function right here. It's totally possible. I'll leave that as an exercise for you if you want to try it out. But we take the reward and then we essentially multiply it by the max Q value out of all the next possible state action pairs. Now, this is only the Q value in this case because remember, this is the policy we're using. Technically, I don't take into account the fact that we're using random actions here, but it's okay. It's slightly simplified for these purposes, and that should be fine. So this is what our actual Q value will look like with our policy. And the reason I bring that up is what you might notice, I should probably go back here. What you might notice is that if this is what our Q value should be, well, now we have a way of generating basically a label for what our Q value should be. So maybe now you could think, maybe if we can estimate our Q value and then use this as an approximate actual answer for what it should be, well, the difference from this approximate and I say this is approximate, we'll pretend like this is the real answer. We can use the difference between the real Q value, what it should be, and the estimated thing that our network puts out as our loss. And if that is what you happen to be thinking, you would be exactly right. So the actual loss function we'll be using is right here. And this is very similar, right? So we take this part right here, we plug it in right here. We plug it in right. I'm right now, I think, noticing a mistake with this. Just kidding. It looks all good. I think that shouldn't be there. Other than that, we're good. As a matter of fact, I'm going to put that back in just for clarity's sake, but there should be a follow-up there. So what are we doing here? Well, we're taking this and we are plugging it right into here. So this is our true value of Q. Now, technically it's not true because we're estimating this too, but we're sort of, I'm not sure if you could call this bootstrapping, but it's the best estimate we have. And this is our current estimate of the state. And essentially we want to make sure that these should be the same value. So we're going to subtract one from the other, and the difference between them squared is going to be our loss. Hopefully that made sense. If not, you might want to rewatch this, or maybe I'll link some other sort of explanations of this. But this is very important. That is why this is what our loss function will be. It's because this is what we expect the Q value to be. This is what we get an estimate of on the right side here. And if they're different, we want to correct that so that they're the same. So the difference between those will be our loss. Okay, I'll stop saying it. And one thing I didn't write here is that when we do calculate the loss and perform gradient descent, we are actually only going to want to do that in respect to the weights of this sort of part of the function right here, which means that we will only, we won't do any back propagation from any part that comes on the left. And I'll show you what that actually translates to in code in a second. But cool, we got that working. So let's actually get to the code. So we're going to go back up to our, I'm going to zoom out again here. That should be good. To our DQN. And I'm not sure if this is the normal way of doing things in PyTorch. I don't think it is, but I'm going to do this anyway because I don't really care. We're going to make a new function called train on batch. And ideally, what you'll have to do is you'll pass in an optimizer, an observation, X, rewards, next observation, terminals, what gamma you want. And ideally, this function should just do the training for us. So the first thing we want to do, right, is we are going to calculate the left-hand side of this. And I'm actually going to copy and paste this over here just so we have a reference while we're writing this. That should hopefully help as a visual aid. There we go. So the first thing is we want to calculate these Q values to start out. So the way we can do that is like this. So we get the Q values from the next observation, right? Because this is S plus 1. And then we essentially just take the maximum Q value. And you see how I have this detach here? That essentially means we're not going to perform gradient descent on this half when we do, we're just not going to, we're not going to take the gradients and perform gradient descent on this particular part. Now, I kind of want to go into more of why, but I think that's a whole nother rabbit hole that we won't go down right now. So now to finish calculating the left-hand side of this, we want to get the terminal mod. So a terminal mod will essentially be a 1 if, I do think I left out one small thing here. In the case of a terminal state, the left-hand side here should just be R of t plus 1. It shouldn't have this extra part because a terminal state shouldn't have any more reward after that, right? So we won't have this gamma times max and so on. So we're going to have these terminal mods that are 1 when we want this side and 0 when we don't want it. And we'll just multiply that part of the equation by the terminal mods. So whenever this is one of the state we're currently looking at is a terminal state, this part will just all become 0 and we will only be left with the reward. So now we've calculated what we're calling the actual Q value. So now we want to calculate the right-hand side right here, the predicted Q value. So we just do a quick pass through our model and we essentially gather the particular indices, right? So if we have a bunch of Q values, right? So we have some 2D array, maybe we have Q value 0.1, and we have 5, 2, 3, 5, and then we have 0.8. You get the point. We have this, for each sort of step in this, we have a set of 4 Q values. And what we want to do is get the maximum from, or not the maximum, we want to get the actions we took from each row. So maybe in the original case, we took actions 0 and then 2. Well, then we would want to grab 0.1 and 6. So we're just getting the actions that are responsible for the path we took, essentially. And that's kind of expressed here in the equation. Excuse me. So now we can actually calculate the loss. And remember, this is just the difference between the two. So we'll do a torch.mean actual QS minus pred, not QS, but Qs. And we will square that. Now what we want to do, that we have calculated the loss, is take the optimizer and do a 0 gradient to reset the gradients. We want to backwardly propagate. I don't know what I'm saying. Do some back propagation, and then apply those gradients. that should be all we need to actually train. You'll notice this is actually fairly simple, which is, I don't know, it's really nice how simple this is, I think, to get such like complex behavior. Or I guess it's not that complex behavior, but, you know, complex results, so to say. So we have that. That is awesome. Now, essentially what we want to do is we just want to go down and we want to actually do the training in our thing here. So the first thing we need to do is create an optimizer, right? So we don't have an optimizer yet, so let's put that right in here. So we're going to be using RMS prop. The only reason is that's what they use in the paper. I'm sure this would probably work fine with Atom or something like that. We're using the same. Did I put the learning rate up? Oh gosh, I'm going to put this up here. Did I put the learning rate here before? I don't think I did. So the learning rate we're using is this right here. This is also the learning rate they use in the paper. And then the update frequency, we're going to do 4. So what is the update frequency? There's one more thing I want to actually put here, and it's the actual DQ in algorithm itself. Except for, here you go. So this is the actual algorithm itself. We might as well read through this really quickly. We've already done lots of this, but essentially what it does is we have some memory, or what's it called? Replay memory. That's our experience replay called D, and our Q function called Q. That's our deep Q network, right? And then we start with S1, we pre-process it, and then we go through this loop for each step. With random probability epsilon, we select an action. Otherwise, we select an action based on the max Q value from our DQN. We execute it, get a new set of states, pre-process that, store the transition in our memory replay or experience replay. And then this is the new part, right? So we've done all that. Hopefully and I'm kind of going through this again, if you ever look at a paper yourself and want to kind of understand what's going on, this is kind of what you'll see, right? It's written in pseudocode. And this is what we have yet to do, this sample random mini batch of transformations. And then we set a y of j, and then we perform a gradient descent step on this, and this is the exact loss function we just coded up. And here it has, as I was mentioning for the terminals, right? Depending on if it's a terminal or not, this part of the equation changes. So we are actually, it's not written in here. I believe in the very original paper, they didn't do updates. They did updates every single step, but that seemed to be a bit excessive. So now we're only doing it every 4th step. So we'll only be performing this part every 4th step. So let's actually go in and do that. So we'll just do it right around the bottom here. And it's actually going to be super simple because we've already set it all up. So train on mini batch. And essentially we're just going to say if the global step divided by the update frequency, which is 4, or modulo that is 0. So every 4th step, we are first going to take a sample from our experience replay. This is the data we get. And then into our train on batch function, we just pass on all that data along with our optimizer. And then it should do, as we just coded, that optimization for us. So let's go ahead and run this. Where should I start from? Let's rerun this first. I'm not sure if we ran it before. And hopefully we shouldn't get any errors, although we did train batch size. Train batch size, where is that? Train batch size, I believe. So I made that 32 in my reference. So this is just how many samples we want to take per training batch, right? So here it says sample random mini batch, or mini batch will consist of 32 samples. Why do I use that? That's what they used in the paper. Although 32 is a pretty good, I don't know, it's just a generally good thing to use. Oh, we got something, no errors yet. Let's give it a couple seconds and see if we get out something else. Nice. You can see the epsilons going down. Now that we're actually training here, I'm going to increase the annealing to take, 100,000 steps instead of just 10,000. So I'm going to talk real with you guys. This takes a long time to train. It looks like it's getting better. I highly doubt that. If it actually gets better right now, I'll be pretty stunned. It usually takes a lot longer. Yeah, it's so what I'm going to do is I'm going to show you my results I have already trained on this previously and show you how it did. So let's move this over here. And the code's essentially the same. So unless there's some weird random typo or something, you should get roughly the same results. Here we go. So this is, as you can see, pretty much the same code, except for, wow, the training has already been done. And these are the results. So we go for 3,300 episodes roughly. By the end of that, we end up with an average reward of, drumroll, around 9 or 10 or 8, something around that range. You can see it's not super stable. And this means that it gets, I believe, 10 blocks on average. Although I do think the blocks higher in Breakout are worth more, so maybe not exactly 10, but around that. Now, you might be kind of disappointed right now, or you might even be thinking, like, what does that look like in a game? So I have a couple things to say, but most importantly, definitely tune in for the next episode because that's where we are going to be covering this. So why is this reward so low? Clearly it's learning, which is super cool, but we want to see it learning. We want to see how it's doing. And, you know, we want to see if we can make it do better, which, spoiler, we can make it do a lot better. So just quick summary of what we did before we wrap up. We made a training function that essentially calculates the difference between the expected Q value and the predicted Q value. We calculate the loss and then perform gradient descent using this function. And then we also edified, we also edited, I don't know why that's there. We also edited our training loop to include an optimizer and an actual portion right here where we can, that's right. This is never mind, where we can basically use that function we made to train. So we're sampling mini batches and training on them. And doing that, instead of getting like 1 or 2 reward per average episode, we ended up getting to about 10, which is roughly 5 times better. So I guess it's not too bad. But if you stick around for episode 6, we will be improving this quite significantly, and we will also be plotting out our results as well as, oh my god, I can't speak, as well as showing the results visually through actually rendering the environment and seeing how well it can do. Thank you so much for tuning in this time. If you enjoyed the video, definitely make sure to like and subscribe. It really helps, and I really appreciate it. Thanks for checking in.